already discussed the concept of charge, current and potential difference. Now, we are going to study how these quantities, current and potential difference, is related in a conductor by introducing a new parameter called resistance. Let's begin. The quantitative relationship between voltage and current for a metallic conductor was deduced by a German physicist, Georg Simon Ohm. He provided a compact and elegant expression that can be used to determine voltage, current or resistance in a circuit, provided that any of the two values were already known. So we get a basic idea about the law deals with. Now we are going to state the law. For that, we are going to imagine a conductor through which the current I is flowing, and let V be the potential difference between the ends of the conductor. Then Ohm's law states that at constant temperature, the current through the conductor between the 2 points is directly proportional to the voltage across the 2 points. For changing the proportionality sign, we can introduce a new quantity called resistance, which is denoted by capital R. Therefore, the voltage is equal to resistance times the current. In the equation, V is equal to R times I. The constant of proportionality R is called the resistance of the conductor, and the SI unit of resistance is ohm, which is denoted by the symbol omega. Let us analyze what are the parameters of the conductor that affects the resistance value. For that, consider a conductor to be in the form of a slab of length L and area of cross section capital A. So here we are placing two such identical slabs side by side so that the length of the combination is 2L, and the current flowing through the combination is same as the current flowing through either of the slabs. If V is the potential difference across the ends of the first slab, then V is also the potential difference across the ends of the second slab. As we know, the potential difference across the ends of the combination is clearly the sum of potential difference across the two individual slabs, and hence it equals to V. The current through the combination is I and the resistance of the combination is RC. From the above mentioned equation, we know that resistance is equal to voltage divided by current. So here the voltage is 2V and current is I. Then the resistance RC is equal to 2V divided by I, which is equal to 2R, where R is the resistance of the slab. From the above equation, we understand that as the length of the conductor doubles, the resistance value also doubles. In general, the resistance is proportional to length. Next, imagine dividing the slab into two by cutting it lengthwise, so that the slab can be considered as a combination of two identical slabs of length L, each having area of cross section A by 2. Here, for a given voltage V across the slab, if I is the current through the entire slab, then clearly the current flowing through each of the two half slabs is I by 2. Since the potential difference across the ends of the half slab is V, that is the same as across the full slab, the resistance of each of the half slab R1 is given here as resistance R is equal to the voltage divided by half the current. Thus we get 2 times the resistance value. From the above equation, we can understand that as the area of cross section of the conductor becomes half, the resistance value double. In general, the resistance R is inversely proportional to the cross sectional area. By combining the above mentioned relation, R is proportional to L and also R is proportional to 1 divided by A, we have got the expression that the resistance is equal to the constant of proportionality rho, which is known as the resistivity, multiplied by the length of the conductor divided by the area of cross section of the conductor. Rho depends on the material of the conductor but not on its dimension. From the above relation, Ohm's law will become voltage is equal to the current multiplied by resistance. So here resistance is resistivity multiplied by the length of the conductor divided by the area of cross section of the conductor. So the new equation will be current multiplied by resistivity multiplied by the length of the conductor, the whole divided by the area of cross section of the conductor. So from the equation, the current per unit area I by A is known as the current density. This is denoted by J. The SI unit of current density is ampere per meter square. If E is the magnitude of uniform electric field in the conductor whose length is L, then the potential difference V across its end is E times L. Using these, the last equation reads as the electric field multiplied by the length is equal to the current density multiplied by resistivity multiplied by the length of the conductor. Or we can say that the electric field is equal to the current density times the resistivity. The above relation for magnitudes E and J can indeed be cast in a vector form. The current density, which we have defined as the current through the unit area normal to the current, is also directed along E, and therefore it is also a vector. Thus, the last equation can be written as the current density is equal to sigma times the electric field. We can represent sigma as a reciprocal of resistivity, which is known as conductivity. Let us summarize what we have learned so far.
Manorama Horizon, learning made simple.